Okay, now that we've learned how to deal with the vectors and their components, we can look at a few examples of how we use F equals ma. So I want to go through a couple of examples. A very, very simple one that everyone's familiar with, that is the gravitational free fall in a uniform gravitational field. And then we may do velocity as well. So let's do that. Before we do that, I want to clear up a couple of misconceptions about force that is often that I often see made in the community. And one of them is the idea that objects or bodies have force. Force is not something that an object has. So if we've got a sphere or a particle or an arrow or whatever it happens to be, and it's moving through the air, it doesn't have a certain amount of force in it. That's just not a thing. Forces are not contained. They're not things that can be contained. Forces, when we talk about forces, we're talking about interactions between systems. So this ball is flying through the air and it might hit a wall. And when it hits the wall will exert forces on the ball, and the ball will exert forces on the wall in accord with Newton's third law. But there's nothing about the ball that carries force. It doesn't have any force in it, and there's nothing about the wall that has any force in it. Um, the force is a way of describing the interaction between the ball and the wall when they connect with each other, and which results in a change in the acceleration, or acceleration and a change in the velocity of the ball. It bounces away somewhere else. So that's an important thing, because what you'll often read are things like the arrow has a certain amount of available force, and in somehow the momentum of the arrow quantifies the available force. I think the term that's often used by some proponents of high momentum archery is something like impact force, or something like that. That if you have more momentum, you have more impact force. That's just not there's It's just not a thing. It's like you're putting the right words into sentences that don't make sense. There's no such thing as an arrow having impact force. There is a force of impact, but that depends on the arrow and the substance that it's hitting, and the exact details of the whole situation. Nothing in the system has force. The force is a measure of the strength of the interaction between those two colliding bodies. So let's with that out of the way, let's work a couple of examples using Newton's law, just to show how this is done. All right, so the first example we're going to do is that of gravity. So here's what you have to do. Again, the process is always the same. You know the force. You determine the force through experiments. You do some experiments. You figure out what the force law is. Then you use Newton's equation to determine how a body under the influence of that force would accelerate. So what we're going to be looking at free fall. So we have some kind of object. Again, it could be a ball or something like that, and it's falling straight down. That's free fall. And specifically, we're looking at free fall with no air resistance. So free fall technically means the only force acting on it is the force of gravity. So we're not going to be thinking about drag or air resistance. We'll add that in at a later time. So the first thing that we always do is we try to figure out, we lay out a system of coordinates. So this is a three-dimensional problem. So what we're going to actually use here is a three-dimensional set of axes. We typically label the x-axis as coming out towards us, the y-axis as moving to the right, and the z-axis as being the one that's going up. And the reason we need to do this is because if force and acceleration are vectors, we need to be able to talk about their components, and we have to assign a coordinate system before we can do that. So the next thing is, what is the law of gravity for an object in free fall? And the law is that the force vector, is going to be equal to minus m times something that's called g. And g is just a constant vector. That's we call it the acceleration due to gravity. We'll see why we call it that in a moment, but it's just a constant. It's just, you think of it as just a constant. It's just like a constant number, except it's a constant vector. So what we're going to do is, the first thing we're going to do is break down f into its components. So what are the components of f? The components of f are Fx, that's the force acting in the x direction. Fy, that's the force acting in the y direction. And Fz, that's the force acting, obviously, in the up and down direction. And what is that? Well, what this equation says, is that F is minus m times g. So what we would have is this first component is going to be minus m times gx. The second component is going to be minus m times gy. And the third component is going to be minus m times gz. Now, from experiment, what you do is you determine what this g is. So the acceleration due to gravity, the constant acceleration due to gravity, what is that going to be? It turns out that the acceleration due to gravity has no component in the x direction. So in the x direction, it's 0. It has no component in the y direction. So in the y direction, it's 0. And it has one component in the z direction, and that is g. And it's about 32.2 feet per second. And now we would normally not use feet per second in the sciences. It's roughly 10 meters per second in SI units, but since everything in archery is done in English standard units, we'll use feet per second as our G here. So what we can then do is write down three sets of equations. We can write down that f of x is going to be equal to minus mg of x, but g of x is 0, so that's just 0. And this is just saying there's no force acting in the x direction, which is obvious. We have gravity. Gravity's pulling down. It's not pulling to the left or right or front and back. And the same thing is true of the f sub y. That is equal to minus mg sub y, which is equal to again 0. And then finally, we have f sub z, which is the force acting in the z direction, and that's going to be minus m times g sub z, but g sub z is just g. That's just something that we call g. So you all may have seen this equation before. It just says that the gravitational force is equal to minus mg, but that's going from the full vector equation of Newton. You have to go through this process to actually get to this. A lot of textbooks start here and just sort of assume that you know the rest of this. But it's really important because very often when we're working with forces, we don't work it in simple cases where multiple components just turn out to be 0. A lot of cases we have components pointing in multiple directions and you have to work with all of them at the same time. So this one's going to be a relatively easy one. But this is it. This is the force. And now we can use Newton's law. So what do we know? We know that the force is also going to be equal to m times a x, m times a y, and m times a z. But we know these components are 0. This is equal to 0 because mgx, we've just said that f sub x is 0. And this one is also equal to 0. So we don't have to worry about those. There's no acceleration in the x direction. There's no acceleration in the y direction. The only acceleration is in the z direction. And this one is now equal to minus mg. So here we have Newton's full equation is, for this case, is minus mg. That's the force, is equal to ma. This looks a little bit redundant, but you have to understand that these are two different things. On this side, we have the force. This is the force of gravity. On this side, we have the response of the body. So what is going to happen to the body in response to being acted on by this force? So we have this force acting down. The force acting down is minus mg equals F. And what we want to know is if this force is pulling on this body, what will acceleration be? Now, this is the case of gravity, which is a special case. In gravity, mass cancels. And so you may have seen an experiment where if you suck the air out of a tube, you can take a bowling ball and you can take a mass of feathers and you can drop them and they both accelerate and fall at the same rate and they hit the ground at the same time. So even though they have the same amount of mass, the acceleration is constant and the mass cancels out. They both hit at the same time. So really we have this very simple, what looks like a very simple equation, minus g equals a. But here is really the beginning of the problem. A lot of times, this is where people don't understand what F equals ma is. F equals ma is not the solution to a problem. It is a little computer that lets you figure out the actual solutions to this problem. Notice nothing about this tells you where the ball will be at any time, and nothing about this tells you how fast the ball will be moving at any time. So let's write this equation in its full glory. Let's remember what a is. And this is technically a sub z, but we're just going to drop the z component because both of the other x and y are going to be 0. So we don't have to worry about x and y. We just are just going to call it a. And what is a? A is the derivative of the velocity in the z direction with respect to time. So this equation is actually more complicated than it looks. It's actually a calculus equation, and it says that the derivative of velocity in the z direction with respect to time is equal to minus g. And now we need to start doing some calculus. So what do we do? This is actually turns out to be a really easy problem to solve. So if you've had calculus, you probably can already see the answer. If you've not, we'll work through it anyway. But what we do is we multiply both sides by dt. We want our dv and our dt on opposite sides of the equal sign. So what we're going to end up with, our next step, I'll come up here to do it, is that we have dv, and again, I'm going to drop the z because it's the only component of velocity is the one going down. dv is equal to minus g dt. And then we do something called integrate. And so what we do is we integrate on both sides of the equation. And this basically says this is the small change in velocity as you go through a small change in time. And what we're going to do is add up all of those small changes to get the overall change in velocity from point 1, wherever we start our stopwatch, to point 2. And same thing here from point 1 to point 2. Let's actually not use 1 and 2. That can be a little bit confusing. Let's use initial and final. So this is our initial point when we start the ball falling, or when we start our stopwatch. This is the final point. This is the initial point, and this is the final point. So we're going to add up all the little changes in velocity and go from what the starting velocity was to what the final velocity was. And we're going to add up all the little changes in time and go from the initial time to the final time. And you would have to take some calculus classes to know how to do this, but it's really pretty straightforward in this particular example. What we end up with is v final minus v initial. So on this side of the equation, we just have, well, if we add up all the changes in velocity, then this whole term is just the difference in velocity between when we started and when we finished. So final velocity minus initial velocity is the change in velocity over this time period, and that's exactly what this thing says. This minus g gets pulled out, so it's actually just going to be minus g here. And the dt becomes the exact same thing. We're going to multiply g by t final minus t initial. Now here we get to make some choices. And we're going to make the choice to set our initial time equal to 0. And this is just simple. We just say that we start our stopwatch at the beginning when we first notice the ball falling, or at the first point that we're actually interested in how it's falling. That's when we start our stopwatch. So it just makes life easier. You don't have to do this. You still get the same kind of the correct equations, but it's nice to just get rid of this. And then we don't have to keep up with TF and TI. We can just get rid of the TF and just talk about T. So T is just the time that our stopwatch reads. Time initial, it reads 0. TF, it's whatever time we're interested in after we see the ball start falling. Okay, and so what we end up here is, if we rearrange this, we end up with the final velocity is going to be the initial velocity minus the acceleration times time. So if you've ever studied any free fall equations, you'll recognize this. This is the equation that tells you how the velocity changes. If you know the initial velocity, you simply subtract from it the acceleration due to free fall, which is 32.2 feet per second, times the time. So you could put in here 5 seconds, you could put in here 10 seconds, you could put in here 12 seconds. And if you know your initial velocity, this will tell you what the new velocity is after that amount of time. So this is one of those things where you could calculate, well, if I drop a penny off the side of the Empire State Building, how fast will it be going when it hits the ground? Well, assuming no air resistance, then all you have to do is say, well, it starts off with no velocity, and then you just take 32.2, negative 32.2, and multiply it by how long it takes to hit the ground, and that will tell you how fast it's going. Okay, so that's not quite finished. We're not done because this equation is for velocity. What we would like to know is if I wait 5 seconds, how far will it have fallen? What is the distance that it will fall? So to do that, we're going to sort of repeat this entire process. So I'm going to erase some of the stuff that we have here. We're going to repeat this entire process of doing an integration. And we'll repeat this, but remember now that v is the derivative of position. Well, we're using the z position, so let's use z because we're falling down with respect to time. So we actually have this exact same equation. We have dz dt is equal to, and this is the velocity at time t, is equal to v initial, the initial velocity minus gt, and we'll do the exact same thing. We're going to take this dt and we're going to pull it over to this side, and then just bring it over here and multiply the whole thing by dt like this, and then we'll integrate both sides. So I integrate here and I integrate here. Okay, so integrating this side is exactly the same. Z final, that's our final location, where on this z-axis we are, minus z initial, that's the location that we started our stopwatch. So zf minus zi is just how far the ball falls. Okay, so zf minus zi is just how far the ball falls. That's what's on the left-hand side. What's on the right-hand side, we have this integral. So it comes in two parts. There's a part here that is a constant term. There's no t dependence here. And then we have a part that's already dependent on time. So we'll handle the constant part first. It's very easy. It looks exactly like what we did when we had a constant g over here. We're just going to have a v initial times time final minus time initial. So again, we're integrating from our initial time to our final time. And here we're integrating from our initial time to our final time. Okay, and then we have a second term, and that second term has this gt, and what it's going to end up being, and again, you'll just have to trust me that this is the correct answer, and you'll get this from doing a little bit of calculus. The correct answer is minus 1/2 times g times, now we have a quantity tf squared minus ti squared. Okay, so this is the full equation that tells us the position as a function of free fall. Now what we'll do is, again, we'll set ti equal to 0. So this term equals 0 and this term equals 0, and let's rewrite the equation. And what it says is that z final, the place that the ball will end up, is going to be equal to z initial, where does it start, plus its initial velocity times the time. So notice the initial velocity times the time tells you how far it's going to go if it weren't accelerating. If it weren't accelerating, time times how fast is going to be where it will be if it's not accelerating. But we know it is accelerating because gravity's pulling it down, so we have to add in some more that makes up for that free fall. And so then we would have plus, except it's not plus, it's minus 1/2. So that's g divided by 2 times t squared. And again, this is an equation that you have probably seen before. If you know the initial location of the ball and you know how fast it's initially going, then you can plug in the initial location, how fast it's going, and any time t, 5 seconds, 2 seconds, 3 seconds, 100 seconds, plug that in along with g, which is 32.2, and what you will get is where the ball ends up. So this is how you would calculate, these two equations are how you would calculate how fast the ball is falling and how far it's fallen after a certain time t. So you might say, okay, I'm on the side of this building, and I'm going to drop the penny off, and I'm going to wait for 4 seconds, and I want to know how fast it's going at 4 seconds and how far has it fallen in 4 seconds. These two equations would tell you that. So notice that's what F equals ma did for us. F equals ma was not the final solution. A lot of times people think, well, you just plug in the acceleration, you get the force out. Well, or you plug in the force and you get the acceleration out. That's a very naive way of looking at this. This is not, the job of this thing is not to just plug in simple numbers and get simple numbers out. The job of this thing is to set up these equations, which are called differential equations, and we use these differential equations to solve for what are called the equations of motion. These are the equations that actually determine how these bodies will fall or accelerate under this force. Now, if you change the force law, if you have something where F is not minus mg, but it's something else entirely, some other examples of force laws would be, for instance, the force of a spring, and the force of a spring is minus kx, which is very similar to this, and would give you a very similar kind of answer. But then you also have, for instance, the drag force. And in ballistics, the drag force is equal to minus some coefficient, I'll call it c, times v squared. So that is a completely different looking force law than this one is, and there are other force laws that are very, very different from these. And so each different kind of force law gives you a completely different set of solutions, different answers. And the way you get those answers is by using Newton's law to solve and take those force laws and solve them for the acceleration and for the velocity to obtain position and velocity as a function of time. So that's what you do with them. I considered also working through the linear drag case, which is where we have drag is equal to some other constant, I'll still call it c, times v instead of v squared. This one may or may not be important in archery. I've heard some people argue that that the arrow going through animal tissue, viscous animal tissue with blood and that kind of stuff, actually results in a force law that's linear in viscosity. So if that's the case, then this one actually would be important in archery. But I've actually already done this one, and I've done this one in a separate video. If you'll look at it, I think the name of it was using calculus to study archery targets or something like that. I can put a link to it in the description of this video below, so you can go through. I go through this exact same process, but I do it for the case of kinetic friction, of sliding friction, constant friction, and then the linear case of velocity and the quadratic case in velocity. I solve all three of those problems. It's a long video, but it does show you the solution and how we use those problems, or how we use Newton's law to determine those kinds of things. So this is the way that Newton's law is actually used in physics. It's not just a simple F equals ma. You plug in an A and you get out an F. That's the most naive way of thinking about it. It's also not something that says that how your arrow is accelerating or how your arrow is moving determines the force. That's completely wrong. You have to figure out what these force laws are. You have to figure out which one of these applies to your system. And once you know which one applies to your system, you then use F equals ma to discover these kinds of equations. So that's the process that we use in physics, and that will help us understand some of the things that we're going to be looking at a little bit later in this playlist on the physics of archery.